Current AI software agents mimic human developers at a keyboard, writing code character by character. When managing enterprise-scale workspaces, this hits a hard mathematical limit. Because language models are probabilistic, they inevitably produce errors. This forces multi-agent swarms into a continuous loop. They generate a text string, run tests, repair the syntax drift, and repeat. In massive codebases, this cycle is expensive. Processing the workspace burns tens of millions of tokens and introduces hours of system latency while agents iterate on broken syntax. The theory of complete compute, or TOC, treats software syntax not as a sequence of characters, but as structured mathematical data. This shift allows the system to store logic contracts, expanding them into functional templates on demand. Recent benchmarks show that a task requiring an 18-hour multi-agent swarm is completed by TOC in under 60 seconds. This speed is the result of a specific architectural choice. TOC operates natively as an abstract syntax tree, or AST, compiler. Compiling logic directly into an AST removes the LLM from the low-level typing process, bypassing the generative token limits of traditional agents. Relying on local compiler execution instead of heuristic guessing verifies the code at the syntax gate before a single byte is written to disk. Replacing text generation with direct AST compilation addresses the root cause of AI-generated syntax errors, providing a stable foundation for enterprise-scale development. To measure the efficiency of this model, we tested it against a workspace containing over 27,000 files and nearly 750,000 lines of code. A traditional multi-agent swarm required roughly 35 million tokens to process this environment. This chart shows the disparity in token consumption. The TOCC Paralaw compiler handled the same 750,000-line workspace using just 12,000 tokens, a 99.96% reduction in generative overhead. The orchestrator achieves this because it never writes character-by-character code. It only produces high-level declarative contracts. These contracts are organized into a structured data format called JSON-IR, or Intermediate Representation. A local dynamic emitter head then translates this JSON-IR directly into a functional Python ASCII object. Programmatically generating these AST objects eliminates the possibility of the structural errors that occur when an AI guesses at code strings. These performance gains are driven by the transition from probabilistic text generation to deterministic data mapping. Rapid automated code generation creates new risks for the software supply chain if the integrity of the output cannot be verified. TOCC manages this by mandating contract storage. The system stores the pure logic of a module, rather than the physical code body itself. Before a logic block is expanded into executable code, it must pass through a 5-gate verification chain. The most critical defense is Gate 4, a dual-hash cryptographic seal. First, a SHA-256 content hash measures exact serialization for byte parity. Second, a semantic hash indexes the logic contract, data flow composition, and AST fingerprint. These hashes are strictly kernel computed. They cannot be hand-authored or bypassed by a developer. Any unauthorized manual change to the files or an ad hoc schema edit will trigger a parity failure, instantly locking the code gate. Locking the codebase at the compilation layer effectively prevents unauthorized tampering and maintains the integrity of the generated source. Probabilistic AI generation often lacks the traceability required by emerging global auditability standards. Regulatory frameworks like the EU AI Act and US Executive Order 14028 demand detailed logs and verifiable provenance for high-risk AI systems. TOC's architecture is designed to satisfy these mandates. This mapping shows how specific compiler features provide the transparency required by NIST and EU standards. Every logic block contains an immutable lineage pointer, known as a previous_version ID. This metadata creates an unbroken record of the module's evolutionary path. Because the code exists as structured data, a compliance auditor can inspect the logical graph definitions to prove the system's exact state at any time. This level of detail offers a clear audit trail that is not possible with the heuristic output of traditional language models. Deterministic compilation shifts AI development into a framework that is compatible with global regulatory and safety standards. When an AI system begins to autonomously rewrite its own operational engine, it creates a risk of unstable self-improvement loops. The NIST AI risk management framework requires continuous monitoring to prevent unintended or chaotic behaviors in these systems. Atomadic addresses this through a primary safety mechanism, the Lyapunov stability check. The system continuously evaluates this equation, requiring the trust metric's derivative to remain greater than or equal to 0. This ensures the verification score never decreases during an autonomous update. If new logic introduces semantic drift, the check fails. A failed check causes the closure operator to refuse to settle, which immediately locks the mutation loop and halts the update. This mathematical anti-laundering invariant provides a hard limit on system behavior. Enforcing these mathematical damping boundaries allows a system to iterate autonomously while preventing chaotic or unsafe outcomes. Building enterprise software by replicating human typing through probabilistic text models is inherently inefficient. As we have seen, the resulting token bloat and syntax drift create significant barriers to scaling. The TOCC architecture demonstrates that deterministic compilation provides a resolution to these fundamental scaling and stability issues. By pivoting from implementation storage to abstract contract storage, the framework ensures that executable code is always a direct projection of its underlying logic. This process is secured by non-negotiable SHA-256 seals and policed by mathematical Lyapunov safety bounds. The result is an environment where theoretical logic and executable syntax are isomorphic, meaning they share the same mathematical structure. Treating code as structured data enables higher generation speeds and zero syntactic drift, while providing the transparency required by global regulatory laws.